And this probably that we have to it's kind of strange. Even more strange because we have an internal seminar on Wednesday and it offers something beautiful. So everyone comes to the internal one and not to the this is a cultural problem. There's some coffee and cakes. But then you have to find it.
The other one is...
Yes, chair of debates in Galileo. I called her from the press conference. She's famous.
Last week when the DI2 came out and they were streaming it.
Okay, so I think it's about time to start. I will introduce you Abbas Askar, who was an astronomicus here in Padova in 2010 and 11. Then he moved on to Poland to work with Mir Kirsch in Copernicus, Nicolaus Copernicus Institute in Warsaw, where he is about to receive his PhD in a month. And then he will move to Lund to work with Melvin B. Davis on a fellowship. So, well, I'll leave you.
Thank you so much. Thank you, Mario. Thank you, Michele, for having me visit Padova. It's very nice to be here. As Mario said, today I'll be talking mostly about my PhD work connected with black hole populations in star clusters using this code for star cluster simulation that I'll shortly describe. So just some slides from memories from this room. These are pictures from my master thesis defense. The pictures were taken by Giovanni Lamura here, and you see some familiar faces. It's Professor Raffanelli and Professor Secco in there as well. So my master thesis supervisor was Dr. Luca Zanzari from the observatory. All right, for the talk today. So for my talk today, I'll talk a bit about globular clusters in general, give you a very brief introduction and about their dynamical evolution. I'll talk about the code for star cluster simulations that I use and from which we got the results, which I will present in this paper. Essentially, these are three projects. One is connected with binary black hole mergers due to gravitational wave emission, and these are the ones which originate in the dense environments of the clusters. Then I'll also talk about a project connected with clusters in which we have an intermediate mass black hole, which makes up for the most of the mass in the cluster, and we call this a dark star cluster. And if time permits, I'll also talk about some latest work about stellar mass black hole subsystems in globular clusters. So let's briefly remind ourselves about globular clusters. These are spherical collections of stars that orbit around galaxies. You see them around, most galaxies have globular clusters around them. They can comprise of up to 100,000 to 7 million of stars. These systems are very old. They're estimated to be 10 to 13 billion years old. And most of the stars are old, metal-poor stars. And what's interesting about these systems is the extremely high density of stars that you see. In the central parts of such clusters, densities can be as high as 10 to the 5 to 10 to the 6 solar mass per cubic parsec. So these are extremely dense systems. And this is why they're interesting from the point of view of dynamical evolution. But of course, they're also important for several other reasons. I've tried to list them here. I won't go through all of them. But the things that I'm particularly interested in are their dynamical evolution and the interplay between stellar evolution and dynamical evolution in these environments. Because this is what gives rise to many interesting populations of peculiar objects. So globular clusters show populations of X-ray sources, blue stragglers, eclipsing binaries, white dwarfs. A high fraction of millisecond pulsars are also observed in globular clusters. Then there has been a lot of recent debate about whether globular clusters contain stellar mass black holes or not, and there are observations suggesting that some of them could have a number of stellar mass black holes in them. Then also the question about intermediate mass black hole and whether globular dense environments can lead to the formation of a massive black hole, more massive than stellar mass black hole in these dense environments. So these are just the main important points of the globular clusters. Now I'll just move on to some introduction about the evolution of these systems. So stellar dynamics, which is something different from celestial mechanics, because here you have a number of masses which have comparable mass, and they're all contributing to the overall gravitational field of the system. And stellar clusters, like globular clusters, are very good environments for studying stellar dynamics. So these are what are described as collisional systems. This means that their evolution is governed by distant two-body interactions. So these are distant interactions between stars. Densities are high enough that the two-body relaxation becomes the main driving force in the evolution of these systems. And typically for a globular cluster, you have a core halo structure. So this is illustrated in the figure there, that you have a core, a dense core surrounded by a halo which is less dense as you go outwards. So there are many important consequences of two-body relaxation. And these are, for instance, evaporation. You can have stars escaping the cluster. You can have dynamical friction and mass segregation. So your most massive stars will tend to lose their energy and decrease their velocity as they try to achieve energy equipartition. So they will very efficiently sink to the cluster center. And also globular clusters are systems with negative heat capacities. So as they're losing stars, they are also becoming more and more dense. So this is this process known as core collapse. And this is when densities get really high, and you can have many interesting dynamical interactions in there. You can have formation of binaries, which prevents further collapse. And these binaries provide energies to surrounding stars. And of course, there are also many other physical processes which are involved. Your stars are also evolving through binary and stellar evolution. You can have very strong interactions. Physical collisions and mergers are also possible in these dense environments. And then you need to take into account the tidal field of the galaxy, which the globular cluster is also, which is also influencing the globular cluster. So there are many important physical processes which determine the evolution of a star cluster. And usually I find this analogy a nice way to understand how globular clusters are evolving if you compare them to a star on a main sequence. So like in a star in the main sequence, you have energy generation through nuclear reactions in the core. And this energy is dissipated outwards through convection and radiation. And then you get loss of energy through radiation and winds from the surface. Similarly, in star clusters, binary interactions in the core are generating the energy to the surrounding stars. And distant two-body interactions, so relaxation, is the main method for energy transport from inside into the outer part of the clusters. And then you get escapers from the clusters. And of course, you're also losing mass through stellar evolution. So this is a nice way to think about how star clusters evolve. So now coming to modeling stellar dynamics. So essentially, you need to accurately deduce stellar dynamics of a realistic globular cluster, objects like globular clusters. You need some numerical methods, and the main method which has been used is the direct n-body method. So here you're basically integrating the equations of motions between all objects. The main advantage of this approach is that it's very accurate, but on the other side, the main disadvantage is that it's computationally very expensive. The computational time scales as a power of the number of objects, to the power 2 to 3. Depending, with some assumptions you can reduce this, but it's computationally expensive. Other approaches include statistical methods, where you have a distribution function describing your positions and velocities of your object, and then you try to evolve this. So for a collisional system, you need the Fokker-Planck equation. You need to evolve the distribution function with the Fokker-Planck equation. However, this is too complicated for a solution in the general case, so you need to make some assumptions to make it manageable. The advantage here is that these statistical methods are fast, but of course the disadvantage is that you lose out on the accuracy, and there are many underlying assumptions which go in. So the method that we use is called the Monte Carlo method, which is a kind of like a hybrid approach to these two models, that it borrows the particle-based approach from the n-body simulations and uses a statistical approach to treat relaxation. And this method was devised by Henon, French mathematician and astronomer, in the late 60s and early 70s. And with this method, I'll underline the basics idea behind this method. So the idea is you have a statistical way of solving the Fokker-Planck equation and treating the distance encounters between the objects. At each time step, you can compute the total potential. You know the radial position of the each star, so if you sort them, you know the total potential. And each star or each object is characterized by mass, energy, and angular momentum. And the idea behind Henon's algorithm is that you repeatedly alter energy and angular momentum to mimic the effects of relaxation. So for this, the main assumption is that you need your cluster to be spherically symmetric. And then the time step that you are interested in has to be much larger than the crossing time. So this is the time needed to go from one side of the cluster to another, which is on fairly short time scales compared to the relaxation time scale. So the time scale over which distant two-body encounters become important. So so you need to be interested in the long-term evolution of the systems for this method to work accurately. You cannot resolve things at the resolution of the crossing time. And between each set of changes, the position of star on its position is chosen, on its orbit is chosen at random. This is the orbit averaged approach. But with the particle-based approach, the advantage here is that you can implement additional processes. You can add you can treat your stars as particles as well, so you can add additional processes which are important in the evolution. So this is what one of our codes, which is based on the Henon's algorithm, does. So this is a code to evolve real-sized star clusters. It has been developed over 20 years of work, started by Studokovic, who was my supervisor's supervisor. And a lot of work in the late 80s was done in improving Henon's approach and adding binaries to it. And as early as the late 80s, Studokovic had already implemented stellar and binary evolution into his code. So stellar evolution, at least, into his code. So the current version of the code, which is known as MOCCA, uses stellar and SSE and BSE codes. These are codes for evolving single and binary stars. This is very important to keep into account when you are realistically modeling an object like a globular cluster. Then for very strong interactions between binaries and single stars and binaries and other binaries, we also need, we use a small n-body code, which is called the few-body code. This code basically is an n-body integrator, and this helps this is very important in making sure that energy dissipated in strong interactions is calculated accurately. Also, we have some prescriptions for realistically treating the tidal field and the escape process from the clusters. And usually we are comparing our results with n-body simulations as well. That's extremely important. And we find that we can reproduce results with some reasonable precision and accuracy. And I'll show you some of the results as follows. So here on the left you have what is known as the Moore's law for n-body and Monte Carlo simulations. So you have the year of publication on the x-axis, and on the y-axis you have the number of objects that were simulated. So starting from the very small n simulations in the early 60s, then you have the CPU era, then you have the GPU era, and these square boxes are indicating published results from n-body simulations. So only very recently in 2016 were we able to use direct n-body codes to simulate a 1 million body globular cluster, and it took nearly a year to run a fairly sparse globular cluster with a lot of with supercomputers and a lot of parallelization. And the same simulation can be carried out, or even with the much larger particle numbers, can be carried out with the Monte Carlo code in a few days or even within a day. So here are some comparisons between the evolution of some characteristic radii from n-body and Monte Carlo simulations. So these are two models simulated with for this Dragon project, which was this 1 million body direct n-body simulation. And then we also simulated the same initial model with the Monte Carlo code. So here you see the evolution of the core radius. So this is going down here. And the Monte Carlo ones are the dotted lines, and the dotted lines very well overlap the evolution of the core radius. So you can't see them too well here. And then here you have the evolution of the half-light radius. So this is also these dashed lines from the Monte Carlo, and the solid lines are from n-body. And again, we have reasonable reproduction in both the cases. Here you have some slight differences in this model, and I'll come to this later. So the idea here is basically to show that the Monte Carlo method is not so far from the n-body methods, and both global properties and properties of specific objects are well reproduced by the method. So what this allows us to do, the speed of the Monte Carlo approach allows us to be able to really probe the parameter space and simulate a large number of models. So this can really help study how the evolution of clusters depends on particular parameters. So the code can be used. This is one of the important applications of the code, and then also the output is quite detailed, so you can make very detailed comparisons, study population of particular objects. So due to its speed, we decided that it would be a good idea to simulate a large set of globular cluster models, which came to be known as this MOCCA Survey Database 1 project. This is a database of about 2,000 globular cluster models that were simulated with the MOCCA code about a couple of years back. And we added a few additional models. So we are probing the number of objects, initial number of objects. We go from 40,000 to 1.2 million. Then we have different metallicities that we probe, which play an important part in the stellar evolution, binary evolution as well. Then we have the primordial binary fraction, different number of initial binaries. Initial binaries can also play a very important part in determining how the cluster subsequently evolves. Central concentration, idle radii, and different structures of the models. And what was essentially quite important was, for instance, for compact objects, is the natal kicks that you give them at birth. So for each model, we simulated a model in which black holes were given high natal kicks, same as neutron stars. This is this is a Maxwellian distribution of velocities with sigma of 265 kilometers per second. This comes from observations of pulsars in the galaxy. So we have models in which black holes get these high natal kicks, and then in the other case we use the fallback restriction, which can significantly lower black hole kicks for black hole kicks. And then for each of the model, we have a 2-segment initial mass function with the lowest mass being 0.08 solar mass and the largest mass being 100 solar masses. So this was the initial setup, and this resulted in the production of around 2,000 star cluster models. About 1,400 of them survive up to 12 giga-year. And here we show these initial parameters which we just sat in the room one day and decided that this would be the initial parameters, but it's important to compare what you are getting out with what we observe in the galaxy to see how realistic these globular cluster models are. So here on the x-axis is the absolute magnitude at 12 giga-years for the models which survive. On the y-axis, you have the absolute magnitude divided by so this is the central average surface brightness, so the magnitude divided by the observational half-light radius. And we find that here the red and the gray plots come from the simulations, and the black points are the observed 150 galactic globular clusters. So our simulations do a good job in reproducing the observed spread of globular clusters. We are not able to reproduce very bright globular clusters. Globular clusters more bright than -8. So these are very massive globular clusters such as omega Cen or 47 Tuc. To probably reproduce them, you need to start out with a larger number of initial stars. Those are not reproduced, but we still reproduce the other observed globular clusters quite well with these initial conditions. So we can say that these models are somewhat representative of what we observe. Initial conditions for these models are somewhat representative of what we observe in the present-day system, present-day galaxy. So now I'll move on to the first project connected with binary black hole mergers due to gravitational wave emissions. So, a couple of years ago, there was the first detection of the first gravitational waves by the Advanced LIGO Virgo detectors. Subsequently, there were more detections, and then this confirms the presence of coalescing binary black holes, and massive inferred masses of these black holes was rather large, about 30 solar masses, and this confirms the presence of relatively massive stellar black holes. So there has been a lot of debate as to the origin of these coalescing binary black holes. They may have formed via binary evolution in the field. Another aspect which I'm particularly interested is in the formation via dynamics in dense environments like globular clusters or galactic nuclei. And then, of course, there are also ideas that these could be primordial black holes and coming from the Big Bang, and then they could also be coalescing and being observed by the Advanced LIGO. So the astrophysical origin remains an interesting problem. And there have been many studies which suggest that globular clusters or dense environments could be important in forming such binary black holes. So as I mentioned earlier, you have important dynamical processes such as mass segregation, which can lead to your black holes, which are your most massive objects in the cluster, segregating to the center where they strongly interact with each other and form binary systems. Globular clusters also have low metallicity, so this can also lead to the production of more massive stellar black holes. And then these can form binaries due to dynamical processes. So a lot of work has been done in this regard recently to see how to use numerical simulations of star clusters to see what sort of how many such objects they can produce and what sort of merger rates can we expect from them. So one of the works, our works in this regard, are a few papers that I've mentioned there. So the idea here was to analyze this large database of models that we have to look for all binary black hole mergers that happen inside the cluster and all escaping binary black holes that will merge within the Hubble time. And then use this data to try to estimate the local merger rate densities for binary black holes that originate in globular clusters. So from all the data that we had, we found that mostly the models which contribute to having black holes, binary black holes, or keeping black holes for a while are the ones in which we have the mass fallback prescription, so black holes do not get high natal kicks. If you give them high natal kicks, then you mostly disrupt the binary system, or they escape the cluster.
Sorry, because there are many models of natal kicks.
Yeah, exactly.
Is the 2002 model based on the mass of the remnant?
Mass of the remnant, okay. Yeah, precisely. So I think for 20 to 30 solar mass initial stars, you end up with 20 to 30 solar mass black holes, according to that prescription.
Yeah, but I mean the natal kick is...
Natal kick is
proportional
to the mass, precisely.
Because it's kind of strong.
Of course, no, you're right. So for the escaping systems, we know from the output of the code what are the masses of the black hole at the escape time. We know the semi-major axis and the eccentricity. So we can calculate the proper coalescence times using the formula from Peters. And for the ones emerging inside the cluster, we need to rely on the binary stellar evolution code, which is evolving all the binaries at each time step in the cluster. So in our analysis, we limited ourselves to black hole binaries in which both the component masses were less than 100 solar masses. And we found that about 17,000 escaping binary black holes merge within a Hubble time, and about 3,435 binary black holes merge inside the cluster from these 1,000 globular cluster models. So there are many interesting ways in which these systems can form in the cluster if you look at an individual object and look into its history. So here is on the left side, I show a diagram showing how a binary black hole forms in the cluster. So you have a 30 solar mass star, two 30 solar mass stars somewhere in your cluster. They evolve to form 25 solar mass black holes. Then they undergo a lot of interactions, flybys, exchanges. In one case, there's also a collision between a horizontal branch star and a black hole, which increases the mass of the black hole to 30 solar masses. And then eventually they end up exchanging and becoming a binary in a binary-binary interaction within 145 mega years. And then you have a binary black hole system with a 30 solar mass black hole, a 25 solar mass black hole, a separation of 22 solar radii, and eccentricity of 0.7. And this will merge within a Hubble time and might show up on your as a detection in the LIGO Virgo. So detectors. So black holes, there's many interesting things which can happen with the dynamics. You can have two black holes in binaries which are separated, and then through an interaction with another star, they could come close enough that they merge through gravitational wave radiation, or you can exchange a black hole with a normal star in a black hole main sequence binary and form a black hole binary. So if you look into Michele's lectures on this, they're very useful and were helpful for me in preparing my PhD thesis as well. So let's talk a bit more about the coalescing, about the properties of these binary black holes that is emerged from globular clusters. So initially, the rate of the merging sources is very high in the first giga year. Most of the mergers which take place inside the cluster happen quite early. 98% of them merge within 500 mega years. For your escaping objects, you have a long tail, and you can have mergers up to present time as well. Most of the escaping binary black holes came from all sorts of models, but the one which merged inside the cluster came from models in which we had very high binary fraction. So these were models in which we had 95% primordial binary fraction. And then for these primordial binary fraction, we have different distributions for the initial properties of the initial binaries. And then these were the models in which you contribute to a lot. But of course, this is a bit complicated, and I'll come to this in a second. I'll first talk about the escaping systems a bit. So roughly 50% of them came from models in which we had binary fractions about 5, 10, and 30%. And then about 8,000 came from, another 50% came from 95% initial models. 95% initial binary fraction models. A lot of the escaping binary black holes formed via dynamics, and a small fraction of, and a number also nearly 40% of them from initial binaries. So typically the escaping binary black holes which evolve from primordial binaries, so in which you have two stars which evolved to form the binary black holes, they had lower semi-major axis values compared to the dynamically formed binaries. So your merger rates at later times, if you look at this histogram, the lower histogram is more dominated by the dynamically formed binaries than from the primordial binaries. And there are important lessons that we learned for this. So firstly, the escaping primordial binary black holes have lower semi-major axis values. Here you can see in the distribution that the primordial binaries have lower values compared to the dynamically formed ones. Most of these primordial ones came from models with 95% binary fraction, and a lot of these binaries had a mass ratio of 1. And binary evolution for such systems can significantly decrease the final separation. And also we learned that the common envelope efficiency parameters are very important in determining the post-common envelope separation of these binaries. And there are a number of reasons why these hard primordial binary black holes escape. So if one of the component black holes gets a natal kick, then the center of mass velocity of the binary can be large enough to escape the system. You can also have mass loss in very tidally filling models, which have a strong tidal field where you can get these escapers. And also dynamical interactions involving these primordial binaries can also result in their ejection. So here are the lessons that we learned. Firstly, is connected with the initial parameter distribution for these primordial binaries. Results can change if you use different distributions for their initial semi-major axes and eccentricities. Then we also found that the default common envelope evolution parameters, which we were using for these runs, produce quite a few binary black holes which are well separated when you use the group by initial binary parameter distribution, but results can change significantly when you change these common envelope evolution parameters, and there are no good constraints on these values. So if we change these values, for instance, with this alpha equals to 1 and lambda 0 in this alpha lambda prescription for the common envelope, you can merge your stars during the common envelope, and then you end up with a more massive single black hole. And what's important is that we find now with the new runs in which we use these alpha and lambda values that you create more dynamical binary black holes compared to the primordial ones. When you merge the objects during the common envelope, then you have a larger reservoir of single black holes, which can then dynamically form binaries with other objects. So this is something we are looking into with new models. But these were definitely important lessons that we learned from these simulations. So the escaping coalescing binary black holes, which dynamically form, can have quite interesting properties, and they form usually in binary single or binary interactions, or through three-body formation, through interactions of three single black holes. And here is the spread of how the mass ratio of these binaries and the total mass looks like. And there are some the observed events from the LIGO. Some few of them are put there. And then you have a nice spread there. And what's nice is that you also have systems in which component black hole masses can be much larger than the one predicted through stellar evolution. So if there is a detection of a binary black hole, let's say in which component masses are larger than 50 or 60 solar masses than what is predicted through stellar evolution, then we can say that they might have had dynamical origins. So this is an important finding of the study. And then we also look at how cluster properties can influence the number of binary black holes they produce. The most simple correlation we find is with the mass. The larger your initial cluster mass is, the larger the number of black holes it has, and the larger the likelihood that you'll form binary black holes. So here on the x-axis you have the initial mass of the cluster, and on the y-axis you have this normalized number of binary black holes that the cluster produces. And also we found that with lower metallicity you get a larger number compared to higher metallicities, but we only had very few models with comparable to solar metallicity. So yeah, this dependence is rather weak, but obviously with lower metallicities you form more massive black holes, and then the likelihood of keeping them in the cluster and for them to dynamically interact becomes larger. We are working on understanding how the initial cluster properties produce and then correlates with the number of binary black holes that they produce. And in this new paper, which will be out soon, we used a limited set of simulations to see the dependence of the number of merging binary black holes on the initial cluster mass, binary fraction, and density. And with this sort of a function, which is defined below, this gamma factor, we find nice dependence on the initial mass density and binary fraction of the cluster. And these results will soon be published as well. So from all these nice results and large number of merging binary black holes that we find our clusters to be producing, we then use some methods to calculate the local merger rates from this data for these events originating from these dense environments. So for this calculation, we needed some sort of estimation for the globular cluster formation rate with redshift. And we also use the total cluster mass. So the basic assumption that goes in here is that the clusters we considered are representative of the globular clusters that we find in the universe. And then using this cluster formation rate and the values and the numbers that we find, and normalizing by the total mass in all the simulations and the number of coalescing events, we find a local merger rate density for binary black holes that originate in globular clusters to be about 5.5 events per gigaparsec cube per year. Here is the distribution of the Church mass that we find from our data, and the rate density for each Church mass. And you can see there with the arrows point towards the detected events, and the peaks in our Church mass distribution can be can explain these, match well with these observed events. Of course, these values can change a lot with your prescriptions from for stellar evolution and progenitors of massive stars. Masses can change, and as a result, this figure can also change, but this is what we have so far from the result. And we think that this rate could be, this is more of a minimum value, and that this rate could be 3 to 5 times higher, depending on factors such as uncertainties in the initial cluster mass. I showed in the beginning that our simulations don't reproduce the most bright globular clusters in our galaxy. So for that to reproduce those, you need to start off with larger initial mass. So if globular clusters initially had larger mass, then the number of binary black holes they could be producing is much larger. If we extrapolate our relation with the initial cluster mass and the number of binary black holes they produce. So this rate is more on the lower side, and it can be anywhere between 50 to 25 events per gigaparsec cube per year. And just to show you a comparison between how the efficiency of the dense environment compares with the field. So if you had 1 million solar mass of stars in the field, and you had 1 million solar mass of stars in a globular cluster, then this is the differences that you get in the production of binary black holes for different metallicities. So at high metallicities, globular clusters can be up to 100 times or 1,000 times more efficient than the field in producing binary black holes. At lower metallicities as well. Of course, in this comparison, it's not fully consistent because there were differences in the prescription used with the field results, but still results indicate that dense environments can be very productive in producing binary black holes, but the problem is not a lot of star formation goes on in dense environments. So this is shown by the figure on the right. This is the estimated star formation rate for globular clusters with redshift. And of course, at more low redshift values, not a lot of star formation is taking place in bound clusters, which form probably a 4 or 6 at redshift 4 or 6. So while dynamical environments are very productive in producing binary black holes, there's not a lot of star formation going on in such environments. So this is the flip side, which decreases the rate contribution from dynamics compared to field results. So we are also looking into now black hole mergers during strong dynamical interactions. And this was another paper that we worked on. So we took some strong interactions involving 3 binary black holes, in which we were calling the few body integrator. And with the original data, we found that out of 500,000 such interactions involving 3 black holes, we only had 1 merger, because these were purely Newtonian calculations. But if you take into account post-Newtonian terms within these calculations, we find that we can get 500 mergers compared to 1. So the capture merger values can be also quite large. And we find that 10% of these can be 10% of these could have happen during these strong interactions, and about half of those will have eccentricities larger than 0.1. So there's a lot of interest these days in finding eccentric mergers through, and this which can be detected by the LIGO detector, and our study finds that we can get those in star clusters as well during strong interactions. So these were the main conclusions from this project, that the dynamical environments are very conducive to forming such systems, and that the local merger rate density depends can be of about 5.5 gigaparsec cube per year, but as I said, this could be higher. because of the many uncertainties in globular cluster initial mass and the mass of the most stellar, maximum mass of the stars in there. And of course, you can also get added contribution from binary black hole mergers that form or merge during strong interactions. But this was the important point that I made, that not a lot of star formation is going on in globular clusters at lower redshifts, so they formed at older times. And of course, it's difficult to infer so far the astrophysical origins of the detected binary black hole mergers. But with future detections and black hole component masses, we could perhaps constrain whether they originated in the dynamical environment or not. And there were quite a few other important lessons that we learned during this project about binary evolution and the initial parameter distribution that you use for binaries. So this was more or less the results from the coalescing binary black hole project. Now I'd like to talk about another project connected with the intermediate mass black hole, in which we describe the evolution of a cluster in which majority of the mass at Hubble time is dominated by an intermediate mass black hole. So from the results of our simulations, we found that about 400 models form an intermediate mass black hole. So this is a black hole in the mass range of 100 to 100,000 solar masses. This is, so far, nothing conclusively has been detected for this mass range. But people have postulated that such intermediate mass black holes could form in dense environments through runaway mergers of massive stars. And we actions and mass transfer in binaries in our simulations. So I'll just skip over this. Here, as I said, we have about 400 simulation models in which we form a mass of a black hole with a mass larger than 100 solar masses. And usually the buildup of the black hole mass can happen in two ways. In these simulations, you have the fast scenario where you start with models which have very high central densities of the order of 10 to the 8 solar mass per cubic parsec. And in these highly dense clusters, very beginning, you can have collisions of massive main sequence stars, which results in a formation of a very massive main sequence star, which then interacts with the black hole. And with very simplistic prescriptions, we then, of how to treat these collisions, we are able to form a massive black hole. And this black hole slowly increases its mass. So there are some examples on the right where in the collision between a main sequence and a black hole, 100% of the mass goes to the black hole, and there are other occasions in which only 25% of the mass goes, but still we can form black holes of 10,000 solar mass through these processes. Then there's another formation scenario in which a single black hole survives in the system during the early evolution, and it stays in the cluster for a while, and then as the cluster is collapsing at a later time, you again get runaway mergers with this black hole, and then it can build up its mass in three-body of and binary interactions, and then you see its mass building up again. But usually through this process, you get black holes of much lower mass, about 1,000, several hundred to 1,000 solar masses. So we had some simulation models in which an IMBH formed very early because they had high central densities, but they also had low galactocentric radius values. So a lot of the mass was lost following the formation of the IMBH, and at present time, the majority of the cluster mass is dominated by the intermediate mass black hole. So we took one of these star cluster models, and we compared, we looked at how it was evolving. So initially it had 400,000 objects, a mass of 2 into 10 to the 5 solar masses, and it was fairly dense in the beginning with central density of about 4 into 10 to the 6 solar mass per cubic parsec. And then at 12 gigayears, we only have about 8,500 objects left in the system, and the mass of the IMBH is about 10,000 solar masses. And then we looked at how it was evolving, and you can see here you have the cluster mass with time, how it's evolving, and how the IMBH mass is building up on the in the blue lines. So essentially, we did this, and we found that most of the mass loss here was taking place due to relaxation and interactions with the IMBH, and of course the influence of the tidal field. But we took the 12 gigayear properties of this snapshot, and we tried to compare it with galactic globular clusters to see if something like this is possible. And then we found that the observational properties, if we look at the mass and the half-light radius, compare well with this interesting globular cluster called NGC 6535. So observers studied this in 2015, and they found it quite perplexing because it has a mass-to-light ratio of around 11. And the idea was perhaps that it has a lot of low-mass stars which are not being observed, and that it could have had a different initial, a bottom-heavy initial mass function. But when they carried out detailed observations of the mass function, they found that actually the cluster has an absence of low-mass stars. So these green points are from observations. So this was also quite surprising. So they were not sure how to explain such a high mass-to-light ratio. So, but such a cluster compares well with our properties for the for an intermediate for a dark star cluster in which this intermediate mass black hole is making up the sufficiently large mass of the cluster. So what we did is we took the 12 giga-year snapshot of this simulation, and we simulated mock photometric and kinematic observations. And to do the photometric observations, we used this code that I've been working on called COCO. It's called Cluster Simulation Comparison with Observation. And the idea is to take simulation snapshots and try to simulate mock observation, idealized mock observations, and compare with the observations. So we can have some sort of direct comparisons with what observers are doing. So essentially, you just need to the simulation snapshot and specifications of the instrument with which you want to simulate the observation, and then you can get the images, and then you can also carry out photometry on them just like observers would. So on the left here, I show the simulated observation of our dark star cluster with COCO, and on the right is an HST image of the cluster 6535. So we thought that this looked quite similar structurally, at least. So then we also carried out mock kinematic observations using this code called Cisco. And this also takes the simulation snapshot and can create IFU observations where you can get the spectra for each spaxel as well. With using this, we created this three-dimensional data cube. So where you also have a spectrum and luminosity information. So these are results from the photometry comparison. On the left, you have the in red, you have the CMD from our dark star cluster model, and in green is the observational CMD from ground-based work. On the right is the surface brightness profile. Green points are the observed ones for NGC 6535. The red points are for our dark star cluster. The shape looks quite similar, even though values are slightly off, but those can be explained by a slightly different methodicity, which NGC 6535 has. And then, of course, age can also play a little role in these spreads. But the important finding from these results, and especially from our kinematic simulations, kinematic observations, was that the signature of the presence of the intermediate mass black hole can be seen within the inner 2 arc seconds from the center of the cluster. So this is in this image on the right. And even if you don't estimate the center of the cluster properly, you can still see the rising velocity dispersion profile in the center, which is predicted from the presence of a massive black hole at the center of the globular cluster. So this was the important finding here. And then I'll just come up with the same conclusion. So we can get globular cluster simulations in which we can form an IMBH through mergers and collisions of stars and black holes. And in certain models, the IMBH can make up for more than 50% of the cluster mass. We took one such model and compared it with observations and found this cluster NGC 6535 to have observational properties very similar to this cluster. So we got observational time based on these results on 2 IFU instruments, Flames and Symphony. So these are very good spectrographs to carry and have been used in the past to study central regions of globular clusters. We are working on the results so far, but it seems that the cluster center available, coordinates for the cluster center available in literature could be very off, because from we didn't get the full data for Symphony because we were on priority B, but from Flames it seems that the central field has very few bright stars. So this will make data analysis harder. So, but we're definitely working on reducing. We might reapply to get time on Symphony with adaptive optics. We could have better observations of this cluster center. But it's definitely an interesting object because its mass to light ratio is quite intriguing. So I'm running short on time, but I'll just quickly talk about the last project and then end. So this is about stellar mass black hole in globular clusters. I won't bore you with the theoretical history so much, but for instance, I can show you what's going on with the numerical results. We simulated from these results that I showed you in the very beginning of these n-body simulations of a rather sparse globular clusters. These were from this DRAGON project. There were two clusters which were evolved up to 12 gigayears with the n-body code. And both these clusters had a large number of stellar mass black holes that survived in them. So one model had up to 1,000 and the other had 245. And the only difference between these two models was the initial mass function. So, and this shows that even something as, even one parameter can really change the evolution of the, perhaps not the global properties of the cluster, but of the specific objects that it contains. And so the idea of this project is to try to look at simulated clusters in which we have a subsystem of black holes, stellar mass black holes, and see how it influences the observational properties of the cluster. So already you can see from here that the cluster with the lower number of black holes has a rather large central surface brightness if you look at the central compared to the models with the larger number of black holes. So this is essentially that the black holes are preventing your luminous stars from segregating to the center, and they're keeping the cluster puffed up. So this this could potentially be a signature for finding stellar mass black holes in globular clusters. So this is what we do. We took some results from the MOCCA survey database. One again, we had about 170 globular cluster models that contain 15 to 800 black holes at 12 gigayears. And these black holes are mixed with other stars. So we defined the size of this black hole subsystem as the radius within which 50% of the mass is in black holes and the remaining 50% is in other stars. And then we tried to look for correlations between this black hole subsystem and the global properties of the cluster. And we find some very nice correlations between the total luminosity and the half-light radius of the cluster, and the density of the black hole subsystem. So this is the top left panel. It's rather small, but on the x-axis you have the mass density of the black holes inside the subsystem, and on the x-axis you have the luminosity, average surface luminosity. So this is the half-light, the total luminosity divided by the square of the half-light radius. And once you have this, then we have other correlations between other properties of the black hole subsystem, such as its density. So essentially, if you know the luminosity and the half-light radius of your globular cluster, you can estimate whether how many black holes it could contain. But of course, you also need to compare other properties. And using these findings, we've identified 29 galactic globular clusters, which could be hosting a sizable population of stellar mass black holes, we think, and a lot of them have already had observational candidates of black holes found in them. So it seems that these results are quite interesting. And then also we are now looking into how we can differentiate between observable properties of models which have a black hole subsystem or an intermediate mass black hole or not. And some of this work I will carry out with Mario Pasquetta here. So yeah, I won't go into the details of these figures. It's still quite preliminary. But this was the basic, most of my talk. And here are some of the projects that we are working on. So there's a huge variety of things you can do with this large simulation of models and the detailed output it produces. A lot of work has been done on cataclysmic variables by my colleague Diogo Bologna using these results. Then we are looking into other binary black holes and other coalescing compact objects that can be produced in these simulations. The future plan is to improve our treatments for binary stellar evolution, for which we are collaborating with Michela and her group here, and then also introduce more realistic procedures and better procedures for treating strong interactions and those sort of processes which are important in determining the evolution of clusters and the populations of objects that they produce. So in the future, we plan on running another database of about 4,000 to 5,000 models, which will probe the parameter space more, and then we can see how the results change with this. So that would be all. I'll leave you with my summary. Thank you so much for your attention.
maybe it's a naive question. The MOCCA Carlo simulation, do you have external gravitational field like dark matter or the distance with respect to a galaxy?
Yeah, so we are treating the galactic potential as assuming that it's a point mass, and that the globular cluster is on a circular orbit, and that the galactocentric radius is defined by the mass of this initial mass of the globular cluster and its tidal radius that we input. So we have galactocentric radius. We are definitely treating the influence. So the mass is the of the galaxies, then the one enclosed within this circular radius. Yeah. So it's a very simple prescription for the galactic potential.
The galactic for dark matter halo?
No other prescriptions for that. No.
It makes sense without dark matter?
Perhaps for clusters which are very elongated or at very high distances from the galactic center, that could be important. But then a lot of more than 50% of the observed galactic globular clusters are within 5 kiloparsec from the center. So perhaps the role of dark matter might not. The galactic potential is definitely, it needs to be modeled more accurately, and in the future there's a plan to use a full 3D potential for that.
Why did you say spherical symmetry?
Spherical symmetry is needed for the method, for the Fokker to have the statistical, to have the relaxation treatment that we use in the Henon's approach. You need spherical symmetry.
It's a strong assumption.
Yeah, but the idea is that if observations of globular clusters to a first degree, you can assume that they are spherically symmetric, but rotation, yeah.
Spherically symmetric.
Now, yes. So this is the point, that the initial model is already assuming that you have a spherically symmetric cluster, which might be 100% accurate. Yeah. And of course, this is something to look at. A lot of people are working in expanding Henon's method to treat non-spherically symmetric system, but of course it gets more complicated.
Or you use n-body.
Or you use n-body. Or one good idea could be to use n-body for a more filamentary structure initially, more fractal structure, and then once you have it achieve some sort of spherical symmetry, then you can use the Monte Carlo to treat the long-term evolution.
I have a comment and a question.
Sure.
The comment is you commented on the fact that star formation in globular cluster is just a tiny fraction of all the star formation, and this is true.
Yeah.
But star formation, the fraction of star formation that happens in denser stellar systems
it could have been
is
higher.
probably much higher.
Yeah.
Because globular clusters are not the only star clusters where dynamics is important. Also, youngster clusters and open clusters are definitely there, and star formation that happens in these systems can be up to 80% of all star formation. So there is also another kind of systems where dynamics can be important.
I definitely overlooked that in the talk, but that is definitely very important. And I think some people do carry out studies on what fraction of star formation took place in bound stellar cluster, and you're right, it can be extremely high. Because right now we are only observing clusters which have survived the initial, evolution in the galactic potential, which was also changing quite drastically with time. So a lot of globular clusters have been disrupted by now. So it could be that in the past formation in them was much higher, and then they are polluting the field with the sources that they are with dynamically formed objects.
Yeah. And the question is, I was quite surprised by the fact that the number of merging black holes depends so dramatically on the primordial binary fraction, on the initial binary fraction that you have in the structure. Because when we run n-body simulations of small open clusters, we find essentially that the number of dynamically formed black holes almost does not depend on the binary fraction, on the initial binary fraction, while the fraction of black holes that form from primordial binaries, of course, depend on the primordial binary fraction. This was published in a paper of 2014 by Ian and Luca. And that maybe the results that we find such a strong dependence on the primordial binary fraction can be related to the method, to the Monte Carlo method. Like
I think more than the method,
I
think more than the method, it's the issue which we had for the high binary fraction models with the initial binary distribution that we use, parameters that we use. So when we are simulating models with 95 or 100% binaries, we are not using the standard in log A distribution for the semi-major axis, but we are using this Krupa distribution. So Krupa in mid-90s had this idea that if all stars originate in embedded clusters, then to explain the binarity in the field, you need to have a higher binary fraction of forming in the embedded clusters. And to explain the observed population that we see in the field, you need these binaries to be dynamically processed. So when you use that initial binary distribution, and you use the common envelope evolution parameters which were default in BSc, the post-common envelope binary black holes that you get are just in the perfect range to merge very quickly within a giga-year or a few giga-years. So if you use different common envelope prescriptions with that binary distribution, you can merge those black holes during the common envelope as well. So I think that really biases the results here, using that distribution and those common envelope evolution parameters.
So what you're saying is that there is also something else that changes in the simulations between the 20%
precisely, and the 100%.
So there may be that these other...
Exactly. So now in the new runs, we have decided that for both the low high binary fraction, the high binary fraction for OB stars, we will use the Sana distribution for the binary parameters. Because I think Krupa in his recent papers is also doing this. He's abandoned the eigen evolution and mass dealing for the high mass component binaries.
It has been suggested some time ago that in the early stages of globular cluster, the most massive stars could coalesce at the center and form supermassive stars that would last a couple of million years or so.
Yeah.
Did you find anything like that in your
Yeah.
simulations?
So definitely, this is the formation channel for the IMBH. So usually what's happening in these very dense star clusters is that you have runaway mergers between main sequence star, and then you get a main sequence star which is a few hundred solar masses.
No, these are talking about 10 to the 4 solar masses.
10 to the 4 solar masses, we recently started doing some simulations with very high particle number and very high initial densities. So we had one test simulation that we did with 20 million stars, in which we had runaway mergers between stars again, and then we formed a main sequence star of about 8,000 solar masses. Yeah.
But how only in one extreme case?
Only in one very extreme case with very high number of stars and extremely high central densities.
But this, since it has been suggested, the supermassive star as a possible origin for multiple populations.
Yes, this has been the reason.
Yeah, but since all globular clusters have multiple populations, they should have all had a supermassive star.
So at some point in the formation, early formation, that's a possibility.
But you find actually only in one extreme case,
yeah,
not in all simulations.
Right, but that is, so that might have, so the formation of the very massive main sequence star could have happened in the proto formation. Because the point we are simulating at the cluster is when, let's say, it has already formed. But if you have a very dense region of gas in your protocluster, where you could form a very massive star, which could then through winds pollute the pristine gas where your lower mass stars are still forming. So this is the idea with a very massive main sequence star, that this star existed during the protocluster phase, but how it formed is of course a big question mark. Yeah.
Just from my understanding, the MOCCA code that you are using cannot be used to simulate objects like open clusters because of the spherical symmetry.
Precisely. Yeah, that's correct. But unless if it's an old globular open cluster, a few million years ago, and you can approximate it to strictly symmetric, then you could use that code. In the past, it has been used for 1 or 2 open cluster studies. Yeah. But those need to be massive open clusters and then little old as well. Yeah. Any questions?
Perhaps one last comment. And you mentioned that n-body codes are much more resource heavy in the computers. And I think there are many more upsides to your code as opposed to n-body codes besides this, right? I mean, you can put more physics in.
Yeah, that's the idea, more physics, and then you can test those without having to wait a long time to get the results. But definitely this doesn't take away the importance of n-body and the direct integration methods. Those are also quite important. And a lot of parameters, for instance, in our case, need to be calibrated with results from n-body simulations. So MOCCA, when it was being developed, was compared with n-body simulations of different mass ranges to see how results are going, and then certain probabilities that you need to compute for interactions, they need to be calibrated with n-body results. So n-body still is this gold standard, as they say. Yeah.
If there's no more questions, we can thank our speaker again.
You were going to be the Seminario user. You know, I think the knowledge Copernicus was 62, and you undertook this project, so I was very happy to.
Thank you so much for all your recommendations and everything. They really helped.